Welcome back. I have a wall here that is underwater. The wall is straight during the first 3 meters, and then it has a shape of a quarter circle which goes from point A to point B. The radius of that quarter circle is 2 meters. The density of water is 1000 kilograms per cube meter. This wall itself is 8 meters long. And now the question is, what is the total resultant force in the horizontal and vertical direction due to water acting on the AB section? And then, where would the center of pressure be on this quarter circle? So first you need to find Frx and Fry, and then the center of pressure. You only have to consider this AB section. Try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now find the total resultant force that acts on this section from point A to point B. This is the pressure distribution that this section experiences. If we look at this point A, then pressure at that point A is the water density times G times 3, because its depth is 3 meters. And of course it's normal to the surface. And then if we look at this point B, then pressure at this point is the water density times G times 5. That's because point B is 5 meters below the sea level, 3 plus 2. And of course they are in pascals. We also know that the length of the wall is 8 meters. And so due to this pressure, we have to find our resultant force that has two components, the x component and the y component, and then we will also find the center of pressure through which this force acts. Now we can find the resultant force either through integration, or we can use the shortcut that you learned previously. Again, this is our wall here. This point here is A, this one is B, and again we're going to create this block here in which you have the quarter circle and a small pocket of water. Due to water directly above this block, you have pressure horizontal equals the density of water times G times 3 meters, so it's 3000 G pascals. Then from the side, this block has trapezoidal pressure distribution. Let's call it P vertical. It increases linearly with depth. So here you also have rho times G times 3, and here you have rho times G times 5. And now, since the length of the wall is 8 meters, you can calculate Fry, the vertical component of the resultant force, due to pH. So we are only considering pH here, and that would be pH times 2, which is this width here. You're multiplying pH by this distance, and times 8, the length of the wall. And so in total you will get 48,000 G newtons. So the pressure is newtons over meter squared times meters from this one times meters from this one. And so you cancel out the meters and you're left with newtons. And that force, of course, points down. Then also, the resultant force from PV would be Frx due to PV, and here you need to calculate the area of this trapezoid. Remember, the distance from here till here is also 2 meters. And so I have this thing plus this thing divided by 2 times 2. That's the area of the trapezoid, but that alone will only give us newtons over meter. So we also have to multiply it by 8 meters, the length of the wall, Then you will have one more meter here, and then you have newtons. And then if you calculate all that, you will get 64,000 G newtons. That force, of course, points to the right. And in fact, this trapezoidal pressure distribution is the only one that contributes to the force in the horizontal direction. So this answer here, it's our total FRX. So we don't need to put this PV here. Finally, we need to find this gravity force that is exerted on this pocket of water. And of course, this point here, that's the center of gravity through which that gravity force originates. In order to find this gravity force, we need the total volume of this pocket of water. Let's first get the total area of the block. So this area is 2 times 2, which is 4 meters squared. You have 2 here and 2 here. So you have the area of the square. Then we need to have the area of the quarter circle. It's pi r squared, which is the area of a circle, divided by 4. So you have pi times 2 squared over 4. And so what you will find is that you will have pi meters squared here. And now the area of this block of water, this one here, it's the area of the square minus the area of the quarter circle, and it's going to be 4 minus pi meters squared. So that's the area of this pocket of water. But to get the volume of this pocket of water, you have to multiply that area by the length of the wall. So by 8 meters. So I'm going to have the volume of this pocket of water equals the area of this pocket of water times 8. And so in the end, this is your result in cube meters. So the mass of this pocket of water equals the density of water times the volume of the pocket of water. So you have kilograms per cube meter times cube meters, and you're left with kilograms, which is the unit of mass. If you multiply it together, then this will be your result. Thus, the gravity force that this pocket of water experiences, it's the mass of it times G. And so this is your result. And of course, your force of gravity points down, just like the force from this pressure pH. Note that now we're actually calculating forces in newtons. When we dealt with the underwater tunnel, we calculated the forces per unit length in newtons over meter. We had WR here, and it was along the tunnel. That's because we did not know, nor we cared about the actual length of the tunnel. We simply knew the tunnel's depth underneath the water, and thus this WR, it was constant along the tunnel's length. So we kept our calculations in newtons over meter, and also in kilograms over meter. That's why we had mass per unit length, where we took our density and we multiplied it by area. So you had kilograms per cube meters here and meters squared here, and so you ended up with kilograms over meter. We did not multiply the density of water in kilograms per cube meters by volume in cube meters, but rather by area in square meters. And that's why we got kilograms over meter and not kilograms. And then later, when we multiplied m per unit length by G, then we got newtons over meter. But now, it's a different story. You know the exact length of your wall. It's 8 meters. So now we are actually calculating the masses in kilograms and forces in newtons. Now we multiply the water density in kilograms over cube meters by the actual volume in cube meters. With that, we get the actual mass in kilograms, and then once we multiply that mass by g, we get the actual force in newtons. And so the point that I'm trying to make is that now, instead of finding something like this, we will actually find 2-point forces that will act on one specific point, the center of pressure. And while we have to find the center of pressure on this arc, if we consider the length of the wall, which is 8 meters, then because of the fact that the shape of the arc does not change in this direction, nor the depth of the arc changes along this direction, in other words, nothing changes as you go along the length of the wall, because of that we know that the center of pressure is located in the middle of this 8-meter distance. So you have 4 meters from this side and 4 meters from the other side. So that's the difference with respect to the previous exercise with the underwater tunnel. Again, the reason why the center of pressure is at 4 meters from one side and from another side is because this pressure distribution here does not change as you move along the length of the wall. And so the total downward force, Fry, it's Fry due to pH, which is this one here, plus Fgw. If you add them together, then this will be your result. And then this is your total Frx, 64,000 G newtons, or if you multiply it by G, 9.81 meters per second squared, then you will get this number. And there you go. Your Fry, it's this one, and Frx, it's this one. And now we simply need to figure out where the center of pressure is located on this arc in 2D. So let's try to find that center of pressure measured from this point, the origin, point O. Let's first focus on X bar CP, so in the horizontal direction. That's the point which this force Fry goes through. Let's first look at this pressure distribution pH. This pH here, equivalently, it can be represented with Fry due to pH, and since it's uniform, it will go through this point here, and since this distance is 2 meters, that means that it will act 1 meter from one side and 1 meter from another side. Next, we want to find the location of the center of gravity of this pocket of water with respect to this point here, the origin. For that, I will first draw a circle here. The radius of that circle is 2 meters, just like here. So the equation of the circle is x squared plus y squared. You have 4 here because you have radius squared, which is 2 squared, which is 4. So here you have to have radius squared. And now, let's only take the first quadrant for the analysis. So this is my quarter circle. I'm going to create a block here. Now, even though I want to find this point here, which is the center of gravity of this pocket of water, I will first do something different. Since the density of water is constant, 1000 kilograms per cubic meter, and also your G is constant, 9.81 meters per second squared, because of that I know that my center of gravity equals my center of mass, which also equals my centroid, the centroid of this area here. So we can simply find the area centroid of this pocket of water, and that will be my center of gravity. However, since we are only concerned with centroids, then it's easier for me to find the centroid by first finding the centroid of this quarter circle, and you will see why in a minute. Let's first define a differential area here. So here I have dx, and then of course the height of it is y, and so dA equals y times dx. So it's the differential area of this column here. And since the radius of this quarter circle is 2 meters, you have 2 here and you have 2 here. And now I can take this differential area and I can multiply by its respective distance from the y-axis. That's my x. And so I write x times dA. And now I want to do the same thing for all the differential areas in this quarter circle. So again, I will integrate this thing. In other words, instead of dA, I can write y dx. And then I will integrate that from x equals 0 meters till x equals 2 meters. Now remember that we have this equation here. X squared plus y squared equals 4. Since we are dealing with a quarter circle, this equation is also valid for this quadrant. So instead of writing this equation like this, how about I say that y squared equals 4 minus x squared, or y equals, and now normally I would have to put here plus minus 4 minus x squared, but remember it just means that the positive square root deals with this section of the circle, and the negative square root, it deals with this section of the circle, but we are only analyzing this quadrant here, which means that to us, only positive square root is relevant. So I'm just going to say that y equals square root of 4 minus x squared. And that y that I have here, it can be replaced with this one here. So I can say that this is my integral. And now, to get my x centroid from this origin here, from the origin of the coordinate frame, I have to take this integral and divide it by the area of this quarter circle. But you already know the area of this quarter circle. It's pi meters squared. So I'm going to divide this integral by pi. In other words, I can simply write here 1 over pi times this integral. And that's because the area of this quarter circle times x bar centroid, it needs to give you this integral here. So we are finding the area centroid just like we have done it before. For example, remember we had a right triangle dam. We used the exact same technique for that. And so if I calculate all this, I will get 0.848826 meters. And of course, I did not do it by hand. I used the Wolfram Alpha online integral calculator. Now, since we're dealing with a quarter circle with a radius of 2 meters, so you have 2 here and you have 2 here, so essentially this entire thing is symmetric about this line here. Because of that, your x bar c equals your y bar c. So this number here, it's also this one. So you don't have to calculate your y bar c separately like we did it in the past. And there you go. You have found your x bar centroid and y bar centroid, and they are both this number here. But remember, it's not our main goal. Our main goal is to find the centroid of this other section measured from this origin here. And an easy way to find it is to recognize that the centroid of this quarter circle and the centroid of the other section, that their combination is the centroid of this square. And so here x bar c would be 1 meter, and y bar c would be 1 meter as well. This square here, it's this square here. You see, you have 2 here and 2 here. So it's logical that the combination of these two area centroids must be the centroid of this square. Now it's also logical that the area of the quarter circle times the area of the other section, it would give you the area of the square. We know that the area of the quarter circle, that's pi r squared over 4, so it's pi meter squared. You also know that the area of the square is 2 squared, so it's 4 meters squared. Thus, the area of this other section, the area of this pocket of water, it was the area of the square minus the area of the quarter circle. It's 4 minus pi meters squared. So we can say that the area of the quarter circle times x bar c of the quarter circle, this one here, plus the area of the other section times x bar c that belongs to that other section. So now we are talking about this section here, and so this distance here, that's your x bar c for this other section. It's this one here. And now all that needs to equal a squared times x bar c squared. So that's 1 meter. And note that in this equation, you know almost everything except this one. This is your unknown. And this is what you're actually looking for. All the other variables you know. And so now you simply need to find this unknown. So I'm going to write here x bar c that belongs to the water pocket, it equals this thing minus this thing divided by this thing. In other words, you have 4 times 1 minus pi times the centroid in the x direction of the quarter circle divided by 4 minus pi meters squared. And if you calculate that, then you will get 1.5533 meters. And there you go. This is the x centroid of this water pocket. It's this one measured from point O. In the same way, you could find y bar c for this water pocket section, but in this case they are equal. You have 2 here and 2 here for the square. The x bar c and y bar c for the quarter circle are the same. Therefore, for the water pocket, your x bar c and y bar c, they are also equal. So now you know where this centroid is located. That's how you do it. You use the fact that the combination of these two centroids, of the quarter circle and the other section, that their combination is the centroid of a square that consists of this quarter circle and the other section. And now, going back to our real water example, you know how the two vertical forces are located with respect to this origin. And here you only care about their horizontal distances. This force here, that's due to this uniform pressure distribution, and its center of pressure is 1 meter horizontally from point O. And then the force of gravity of this pocket of water, we found out that horizontally it's 1.5533 meters from point O. So we have two vertical forces. But of course, we want to have one combined vertical force and its combined center of pressure measured horizontally from point O. In other words, we want to get the center of pressure through which this FRY goes. To find that point, you follow a similar procedure, but instead of multiplying areas with distances, you multiply forces with distances. So I'm gonna have Fry due to pH, this one here, and now I'm gonna multiply it by 1 because I have 1 meter here. Then to that I will add the product of the gravity force that the pocket of water experiences here and its center of pressure from point O, which is this one here. As a result, I need to have the product of the total combined Fry and its center of pressure horizontally. I know my Fry, it's this one here. I know my FGW. We found it to be 8,000 times 4 minus pi times g, and that was in newtons. Then we found this force due to pH to be 48,000 times g newtons. And so that means that my combined X bar Cp is going to be the sum of these two products multiplied by 1 over Fry. So this Fry goes away from here and it will go here. And if you make the calculations, you will find that X bar Cp equals 1.0693 meters. And there you go. Your total Fry vector goes through X bar Cp, that is this number here. And of course it's measured from this point of origin, O, and you measure it horizontally. So it's gonna be somewhere here, a bit more than 1 meter. And now that we have our X bar Cp for Fry, the final step is to find the Cp for Frx. For that, we have to find the combined center of pressure for this trapezoidal distribution. But we have already done something like that. I'm gonna divide this distribution into a rectangular distribution and a right triangle distribution. You know that for the rectangular distribution, the center of pressure will be 1 meter because the total distance here is 2 meters. And you also know that for the right triangle distribution, this distance is 1/3 of 2 meters. So it's gonna be here 2 over 3 meters. And now we have to find their combined center of pressure. Remember that this side here is rho v times g times 3 meters. The other side is rho v times g times 5 meters. It means that this side here, we can say that it's this one minus this one. So it's gonna be rho w times g times 2. It's the difference of this point and this point. And now I'm gonna calculate the area of this rectangular distribution. You have rho v times g times 3 times 2 times 8. So this gives you the total force due to this rectangular distribution. 8 here is the length of this wall. This 2 here is this distance, the vertical distance. And then this one here, well, that's just this uniform rectangular distribution in pascals. And so all that will give you Frx due to this rectangular distribution. And then that I will multiply by 1, which is the center of pressure of that rectangular distribution. Then plus, and then this one, that's the total force in the x direction due to this triangular distribution. So it's due to this one here. And so what I will do now, I multiply it by its center of pressure, 2 over 3. And so all that, it needs to equal the sum of these two forces, which is the total force due to this entire trapezoidal pressure distribution, times their combined center of pressure in the y dimension. And so you only have one unknown here, this one here. Everything else you know, right? So if you find this unknown, then you will find that your y bar Cp equals 0.917 meters. It's an approximate value. A more precise value would be 11/12 meters, but approximately it's 0.917 meters. And there you go, you have your y bar Cp, your general Cp through which your total force in the x direction goes. It's measured vertically from point O, and it's logical that it's somewhere in between 1 meter and 2/3 meters. And so, this is your total FRY at x bar C equals 1.0693 meters. Then this is your total FRX at y bar C equals 0.917 meters. And so in the end, this here, that's your center of pressure. So if you were to take the resultant force of your FRX and FRY, then this FR, it would also go through this center of pressure. So instead of FRX and FRY, you would simply have FR, and its line of action needs to go through this center of pressure. So that's how you deal with structures that have curved surface and that are under the water. Thank you very much.